Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 44, we will cover the second part of link assignment. The different concepts that we will cover in this particular lecture are on user equilibrium assignment, system equilibrium assignment, stochastic assignment algorithms such as using simulation methods like Burrell's algorithm, and proportional stochastic method using Dial's algorithm. And we will also look into what is stochastic user equilibrium. So, when we talk about user equilibrium assignment, we have already discussed the basic concept earlier. Wardrop's principle states that the concept of user equilibrium is based on the fact that individuals choose a route so as to minimize his or her travel time, and such a behavior on the individual level creates an equilibrium at the system or the network level. So, this was Wardrop's first principle. That means everybody chooses, as per their knowledge, they will choose the shortest route. And because everybody is doing the same and there is difference in everybody's choices, definitely it creates a system equilibrium where everybody is divided amongst in certain routes. And flows on links whose travel times are assumed to vary with flow are said to be in equilibrium when no trip maker can improve his or her travel time by unilaterally shifting to another route. That means in all the routes the travel times are same. The routes that are used, the routes that are not used, there the travel time is of course higher. So, all the routes that are used, their travel time remains same, and then there is equilibrium estimated. So, in this particular example, you can see there is between O and D, there are route 1 and route 2. These are two routes, and the total demand from O to D is 110. So, if I see on this particular graph, we see that this is volume on the route in this direction, and this is the travel time or speed along in that particular route. So, in the first route, or the speed is around 40, this is the free flow speed, and then in the second route the speed is 30. So, automatically people will start using the second route because it is more faster. And once they start using the second route, automatically at one point of time, when it reaches almost it's like around 100, or the total demand is O to D is around 110. So, gradually we see that at around this point it starts increasing, and after a certain time the travel time increases, and when it reaches around 100 we see that it has almost reached 40. So, that means for the next 10%, will they be assigned to this route 2 or they will be assigned to route 1. So, depending on the travel time of then this persons, they will compare that, well, this is also 40 and this probably the route 2 has become 42. So, they will get assigned to route number 1, and they will continue to do that till till it again increases, and then it becomes maybe 42 as well, and then again people may fall back to route 2. So, this is the process where eventually we find that the travel time in both the routes are more or less has reached the same level. So, it is the same travel time. And any other route which is not chosen, suppose I add another route like this route is not chosen at all, and there the travel time remains higher, like suppose it is 65. So, here this route is not chosen at all and it will remain as it is, and that means this and that means no volume would be assigned to this particular route. So, we can also say if all trip makers are rational and perceive cost in the same way and seek the same objective, that is shortest, they want to reach using the shortest path, and it is a single, that means we are considering a single user class. That means everybody is having the same perceptions about cost, same preferences about cost or time and so on, which variables they will consider when they will choose a particular route, or there is no stochastic effect. That means there is no variability among the population, everybody wants the same thing. Then the principle could be also stated as, under equilibrium conditions, traffic arranges itself in congested networks such that all used routes between an OD pair have equal and minimum costs, while all unused routes have greater or equal cost. So that means for a given OD pair, we can mathematically express it as Fk into Ck minus u equal to 0 for all k, and whereas Ck minus u is equal to 0 for all k. So what it means is, Fk is the flow on path k, Ck is the travel cost on path k, and u is the minimum cost of travel for that particular path. So in equation 2, we can have two states of this Ck minus u. We can have two states where if Ck minus u is equal to 0, that means Fk would be greater than equal to 0. So that means used paths will have same travel time. Whereas Ck minus u is greater than equal to 0, then from equation 1, Fk is equal to 0. And that means there is no flow when Ck is actually unused paths with higher travel time than minimum cost path. So that means when the travel time is higher than the minimum cost time, then flow is 0. And when used path is the same as the minimum cost time, in that case Fk is greater than equal to 0. So that is what this actual equation signifies. So we are creating some assumptions, we are making some assumptions. The user has perfect knowledge of the path cost. First of all, the entire user group is 1. So every one of them has got perfect knowledge of the path cost, which is, again, this is an assumption. Travel time on a given link in a function, travel time on a given link is a function of the flow on that link only. That means travel time is affected by the total volume in that link. It is not affected by the volume in other links. So that is also we are assuming that. And travel time functions are positive and increasing. So these are the three assumptions that we are starting with. So let's see an example, and then we will see how to solve it. So let us consider in this particular figure, T1 and T2 are the travel times on route 1 and 2 in minutes. So this is T1 and this is T2, and this is route 1 and this is route 2, and we are going from 1 to 2, and x1 and x2 are the traffic flow in vehicles per hour on route 1 and route 2, x1 and x2. Assuming this usual equilibrium conditions, an hourly flow rate of 4500 vehicles per hour, determine the travel time on each route, traffic volumes on each route, and the total system travel time. So we introduce a new term which is called total system travel time. Now this is a very famous example. This has been used in many books as well as in many lectures by different professors. So this will actually give you very easy understanding of this equilibrium process. The solution, how we do that, how we consider it is, first we considered the basic flow conservation identity, that is the total flow, that is x1 plus x2 is equal to 4.5. Now 4.5 is basically 4500 vehicles per hour. We have taken in thousands of vehicles per hour, so that's why we have taken 4.5, just to make our calculations easy. So Q is the total traffic volume between the OD pairs 1 and 2, and x1 and x2 are the two routes. So overall, in between these two routes, the total flow would be 4.5. So this is final. Now let us check if equilibrium conditions are possible or not. That means if I load the entire traffic volume into one of the corridors, let's see what happens. If all traffic is assigned to route 1, suppose this one, then T1 is for 4.5, that is for the travel time for volume of 4,500 vehicles per hour. Using the formula, we get around 24 minutes. That means T1 is equal to 6 plus 4 into 4.5, which comes to around 24 minutes. Whereas T2 is 0, that comes to around 4 minutes. That means this is x square. So you can understand that when travel time increases, then suddenly when flow increases, then there is drastic reduction. That's why there is a squared term. There is no squared term, so it's more stable. So in this way, in this particular equation, if I put x2 equal to 0, we get t2 equal to 4. So we can see that 4 and 24 is not same. So this is not equilibrium condition. So there is chance, that means equilibrium has not been achieved if I assign all in one side. Then T1, if we do the other one, that is T1 equal to 0, and we get equal to 6 minutes, and the other one becomes T2 equal to 4.5. We use 4.5 over here, we get 24.25 minutes as the travel time. So you can understand that this one is lower than 24 minutes. So automatically that means there would be more traffic in this particular route. So that's why there is no equilibrium, this route doesn't match, and also this one is lower than this one. We are assigning everything to this one, so this particular link x1, so that's why the travel time is increasing, whereas the other is small, which actually, that means actually this would have been chosen. So in this way, if I see, that means equilibrium is not yet possible. Now let us assume Wardrop's equilibrium rule, that is T1 will be equal to T2, right? So that means if I equate these two equations, then we get 6 plus 4x1 equal to 4 plus x2 square. So since now replacing x1 by 4.5 minus x2, which is because x1 plus x2 equal to 4.5, we get this form of the equation, and then if we solve for x2, we get x2 equal to 2.89, and x2 is 2.89, means x1 is 4.5 minus 2.89, which is around 1.6. So now I put these values in my travel times, and we estimate travel time 1 is equal to 6 plus 4 into 1.6, which comes to 12.4 minutes, and T2 is equal to 4 plus 2.89 square, which also comes as 12.4 minutes. So that means this is the equilibrium time. That means at this is the travel time taken by in these two routes. Now let us find that, and of course when we do that, then automatically we can also estimate the total, and this is the total flow in x2 and this is the total flow in x1. So 2.8, actually it was 899. So 2.899 is the vehicles, this is in thousands vehicles per hour, and 1.6 thousands vehicles per hour is the flow in x1 and x2, and these are the corresponding travel times, which is same as per Wardrop's equilibrium. So this is Wardrop's first equilibrium. So now I said that we will estimate something new. This is called total system travel time, where we are multiplying x1, that is the total flow, into the travel time. This is T1. T1 is estimated for x1. So T1, we have replaced x1 value. So using the same x1 that we are putting over here, and we get like 2899 vehicles per hour into 12.4 plus 1601 vehicles per hour into 12.4, that is total 930 vehicles per hour. So this is the value that we get, and this was in minutes, we converted into hours, so it has become 930 vehicles per hour. So this is the total system travel time that is being taken. So this is travel time into the total volume. So this is the total time spent in the system. So this is a measure, as you can understand, which actually talks about efficiency of this particular system. Now, as per the first equilibrium, now conditions of Wardrop. So in this one, we can also solve it mathematically. So we have just solved it using a small example, but there could be much, the number of links could be many more, and also one link is composed of, one route is composed of multiple links. So to give it a formula, and what we need to do is we need to actually determine the total area under each of these flows. So that means the solution, that means using calculus, we can actually solve this, and this could be derived solving an equivalent nonlinear mathematical optimization program, where we minimize z, where it is equal to summation of it's for all A is A to XA, these are for different XA is the total volume, and then this is TA at XA. So, we take the integral of TA XA, this is travel time, and this is minimized because all the along all the routes the total travel time would be same. So, for different and the volumes would be also considered. So, we do it for all the different volumes as well. So, that means because all of them are same, if we solve for this, then basically we are trying to find the area or the total area when we are taking our integral under each of those curves that we were discussing earlier, that is the total travel time was increasing. So, in that way this actually can solve and give us the result. We can solve it mathematically as well and get the result. So, over here you see k is so this is minimized z subject to summation of k f k r s, where f k is the path and x is the equilibrium flows in link A, and T A is the travel time on link A, and F K R S. So, T A and X A are link travel times and link flows, and F K R S is the flow on path K connecting OD pair R S, and Q R S is the trip rate between R and S, and delta R S is a definitional constraint, and it is 1 and 0 according to if a link belongs to a particular path or not. So, that means we will keep on adding the links, and if it will be multiplied by 1 or 0 if that link is within a particular path or not. And what we are doing is XA, we are saying XA is always greater than 0, FKRS is always greater than 0, and XA equal to summation of R, S and K, and this is where we are multiplying that particular if that link is within that path or not, and this is FKRS for all R, K and R, S and K. So, this is done, and then we are taking a summation of all the paths FKRS equal to, and this becomes QRS. So, this is the total, QRS is the total flow. So, this is actually extending our first two equations, where we said that the travel time has to be same, and we were talking about the paths as well. So, this is actually we are saying that all the travel times are going to be same, and that is what we are trying to minimize the travel time. So, anyway, so this is the this we need to solve, and similarly we will see another extension of that particular mathematical form, where we see in Wardrop's second principle, which talks about system optimal assignment or SO, where Wardrop proposed an alternative way of assigning traffic onto the network, which is the second principle or called system equilibrium, where transport planners and engineers who are trying to minimize traffic or manage traffic or minimize travel cost over an entire city, for them this could be the principle that they could actually focus on, and by managing travel times or by managing signals or managing flows in different corridors, people may try to achieve that overall total travel time spent in the network is the least. So, that means there we have to multiply the total volume in each link into the travel time of each link, and this has to be minimized. So, if you remember from our previous example that we discussed, that Sx equal to x1 t1 x1 plus x2 t2 as a function for x2. So, this is the total system travel time, where we have got the volume and the time spent. And see, same way we were minimizing in the usual equilibrium, over here we are minimizing z, where the total xa into Ta for of course xa. That means this is flow into travel time that is being considered. So, xa is equilibrium flow in links A, Ta is the travel time on link A, and so xa is the equilibrium flow because it is a system equilibrium, and FRS K flow on path K connecting OD pair RS, this all remains same. QRS is the trip rate between RS, and delta is a binary function equal to 1 when link belongs to path K or otherwise. So this part, that everything else remains same. Only thing is we are minimizing, instead of just TAXA, we are minimizing XA into TAXA. So this is the difference in the system optimal part. So in under social equilibrium or system optimal, we say under social equilibrium condition, traffic should be arranged in congested network in such a way that the average or total travel cost is minimized. So that means the overall travel cost of the system is minimized, and this is a process where we not look into every user minimizes the travel time. That means some user have to experience more travel time compared to others, but overall the system travel time decreases. And over here we minimize XA into TA, which was in the earlier case just XA, just TA for a particular link. So in system equilibrium assignment, if I take the previous example, we have got x where T1 equal to 6 plus 4x1 and T2 equal to 4 plus x2 whole square. Now in total system travel time, this was the formula x1 into T1 x1 plus x2 into T2 x2. So x1 we can replace T1 x1 by equation this one 6 plus 4x1 and T2 x2 by, this is the equation 4 plus x square. So Sx equal to 6x1 plus 4x1 square plus 4x2 plus x2 cube. So again replacing x1 with 4.5 x2, we get Sx equal to, we get this particular form which leads to x2 cube plus 4x square minus 38x2 plus 108. So this is the total system travel time that we need to minimize. So to minimize system travel time, we have to first, again as per the principle we discussed earlier, we have to set the first derivative to 0. So we take ds by dx2 of x, this is equal to, we take the first derivative of this particular equation, which is x2 cube, that is 3x square plus 4x square, that is 2 into 4, 8x2 minus 38. So this one is constant, so 0. So this becomes 0. So when we solve this, again it's a x square form, we can solve this, and we can we get x2, like the last time we got x2 equal to 2.467 and x1 equal to 2.033. So this is the volume along x2 and this is the volume along x1. When I put these volumes into the travel time calculation, so T1 becomes 14.13 minutes and T2 becomes 10.08 minutes. So you see this is totally different from what we have established earlier. Last time it was 12.4 minutes in both the links, and the traffic volume was also organized in accordingly. Over here the travel times are different and the traffic volumes are also accordingly different. And when I compute the total travel time, total system travel time, we get using x1 T1 into T1 plus x2 into T2, we get 893.2 vehicles per hour, which is less than the usual equilibrium assignment, where we were getting something around 930 if I remember correctly. So that is a reduction from the usual equilibrium this total system travel time value. So if I go for system equilibrium, obviously this is the minimum cost that is achievable over the system, but it also means that not all people would be using the shortest route. So some people are using a longer route, so that the overall system is more stable, or overall system, the shortest the overall system cost is least. So this is system equilibrium, which is a little bit different from usual equilibrium. But again, this is also our transport planners are actually will focus to reduce the overall cost of the system. So probably for them this is the method that they can also employ. Then once we are looking into the equilibrium assignment, then we look into the stochastic assignment algorithms. So stochastic methods consider variability in driver's perception while choosing a route. That means now, till now we were not talking about the each individual driver's variation in perception. So drivers choose to minimize cost or a composite measure. It could be distance, travel time, generalized cost, or like that. And stochastic, so they could consider to reduce any one of them. and stochastic method considered alternative routes between OD pairs. That means here it is not based on system equilibrium, it is just considering that based on the knowledge of the drivers or the perception of the drivers about the shortest path, they will choose different routes, and that will lead to a certain form of assignment. So there is no equilibrium that is being considered at this point of time. So there are two methods. One is simulation based method, which considers stochastic Monte Carlo simulation, which considers the variability in the perceived cost, and this is achieved by Boodle's algorithm. Whereas there is the proportional stochastic methods, which considers flows are allocated to alternative routes, and the proportions are calculated using logit or similar equations. Logit or similar equations means we use the cost exponential to that cost of that particular route, and here we use Dial's algorithm. So these are the two common algorithms which we use in stochastic assignment methods. So in simulation based method or Boodle's algorithm, each link in a network, we consider a cost for each of the links, where there is a fixed cost which is called the engineered cost, and then there is a subjective cost as perceived by each driver, and that is actually taking care of the variation how a driver perceives a cost. So engineered cost is basically the mean. So this is the actual cost, you can say, and then distribution of perceived cost are assumed to be independent, and this is because of different perceptions of different drivers. Some people may feel the cost over here, another over here, some people may over here, and in this way, so more or less it follows some distribution. So Bournel assumes it's called a uniform distribution, whereas some others have also assumed something called normal, or some people have also assumed normal distribution. So in that means this distribution is basically the distribution of the observations of the different perceptions of each individuals regarding different link cost. So drivers choose the route that minimizes their perceived route, which is sum of individual link cost or link cost, and so that basically means that drivers will choose the route that minimizes their perceived route cost. That means whichever route they feel to be the least cost, they will choose it, and basically route cost is basically a sum of individual link cost. So for what is required is select a distribution. We have to select a distribution. It could be normal distribution, uniform distribution, and the spread parameter for this distribution sigma for the perceived cost for on each link. And then what we do is, because of this distribution, we can understand that some people will be choosing over here, some people will be choosing over here. So we have discussed earlier in some of our earlier lectures that we can use random variables to pick up that, okay, what would be the distribution that would be chosen for a particular person, because we want to assign one person to one particular cost what he has felt. So based on the distribution, we can pick up a random number and see, using that random number, what is the cost a person actually feels for a particular link. So divide what we can do is, so that means each individual person has to pick cost for each link, and that will lead to different shortest path for each of this particular for different routes. Now if I do it for every individual, then it's a huge amount of computation. So instead we divide the population along each OD pair into n segments, like we were dividing it during incremental methods. We also divide it over here into n segments who perceive the same cost. That means we assume that this group of people will assume the same cost for this particular link, and in most cases n is just equal to 3 or 5. So that means there are 3 or 5 alternative routes maximum. So Boodle's approach generates cheap routes more often as a result of stochastic variation in the link cost, because we are following a distribution. So in most cases, and we are using random numbers, we will end up with the actual link cost more, and that means that random number will be more appearing towards the mean, and automatically we will get cheaper routes in most cases. But sometimes we will also get costlier routes as well, but the chances of that is less. So let's see the algorithm, where what we do is we first do the network, we first code the network coding the network means assigning the different characteristics of the network. We calculate the initial link impedances, the initial travel times, and then using a statistical distribution for what people perceive about each of the links, the cost of the link. So, we already know the mean value of the links, the link impedance. Then we simulate the link impedance. We pick up a random number, see where it fits into the distribution. Accordingly, we choose that particular value from that distribution, and we adopt a particular travel time for a particular link for that group of individuals. And link impedance is there is a random variable is being assigned, and using that new link value, we build a network, and then we search for paths in that network, and we assign trips for this group of individuals from the trip table into this particular paths that we have now determined. So, we accumulate the link volume, and then we update the link impedance based on volume by capacity ratio, and once we do that, then our prescribed number of iterations are completed. Then we again, if it is not, then we go back and again simulate link impedance for the other group of people, and so on. If it is completed, then we move on and calculate impedance based on speed and based on number of iterations, and we get output assignment information. So, this is our Boodle's algorithm. So, link cost distribution applied to a link of cost C, you can see C star equal to C plus into 1 plus yi into d, where C is the random value of link travel cost. So, this is the random cost that we are assigning. Cost means time or actual cost, where C is the actual link travel cost, this is the mean observed cost, and yi is the standard normal distribution. You remember standard normal distribution. So, d is the diversion factor that we adopt, and this actually gives us a random value. We can use this particular factor, and then from that we can get a random cost value for a particular link, which is of course in most cases, because of random number, it will be near to the actual cost, more often near to the actual cost, and then we can use this cost to build that network that we are talking about. So, let us in the algorithm, first n is equal to made into 0, then we update n in n plus 1, this is number of iterations, n is the number of iterations that we will do, this is the and then or you can say that this is how we will break the entire population as well, and then compute for each ij pair, compute perceived cost for each link by sampling from the corresponding distributions of cost by means of random numbers, that we will do, and then build the minimum perceived cost from I to j and assign Tij divided by n trips. So, n groups are there. So, that is why so many number of iterations we are using. So, Tij and divided by n is the total trips divided into so many parts to it, and accumulating and we put it in the network and accumulate the resulting flows onto the network. So, if n is equal to n, the number of iterations matches the total number of groups, then we stop, otherwise we go to step 2. So, that means we update the number of iterations from n equal to n plus 1, and then we keep on doing the same thing. That means we choose another set of new values for the link, and then create the shortest path out of that new values and assign this particular group of people to that shortest path, and we update the entire traffic volume of that particular network. So, in this way we will come to a point when all the traffic volume has been assigned to the network, and that will be how we actually use this in Boodle's algorithm, we actually do the assignment. Then in the next method, where we do proportional stochastic method, there theoretically this method splits trip arriving at a node between all possible exit nodes. That means we divide the number of trips going from one node to other node. That means it splits the trip into different pathways. But when it is implemented, it is done like the division of trip arriving at a node is actually based upon where the trips are coming from. That is the number of entry points. So, if I have origin I and destination j, so this is my point B, and this is the trips are arriving from A1, A2, A3, A4. So, this is the previous node, and we will divide that total number of trips and using something called a splitting function factor f1. So that is how we had split the number of trips based on the possible entry nodes a1, a2, a3 and a4 between origin I and origin destination j, and this splitting function is defined as fi equal to 0. That means there is only there is no split, there is only one flow if dai is greater than db. dai means the total distance from I to ai. So this is the total distance, and dai is, if dai is greater than db, that means it is db is on the shortest path. If dai is greater than db, that means it is not on the shortest path. So that means that f1 will be equal to 0. This ensures that the trips are allocated to routes which take them efficiently away from the origin. So that means this is taking the trip away from origin I, but it is done in an efficient way through shortest path. So if dai is lesser than db, that means dai is actually shortest path. That means because it's a node before db, so if it has to be less than db, then dai is less than, then fi is somewhere between 0 to 1. That means there is division in the trips, where dai represents the minimum cost of travel from origin I to node ai. So the trips tb that passes through b are divided according to equation faib, where tb into fi divided by summation of fi from so this is all fi. So this is the way we divide the entire trip. So this is how the trips are being proportionately divided into different routes. Now in Dial's algorithm, the algorithm proposed by Dial, this implements a logit route choice model with parameter omega at the network level, and at the network level identifying a set of efficient paths connecting each OD pair. So that means when there are different route choices and using a logit type of formulation e to the power of a particular amount of cost, that actually is used, because that's a sort of impedance that is used to divide the number of trips between the different routes. So the splitting function is defined as fi equal to exponential to the power minus omega delta di, where delta di is the extra cost incurred in traveling from origin to node b via node ai, the same concept that we just discussed, instead of via the minimum cost route. So this is, so instead of minimum cost route, we are traveling along a different route and there is some extra cost to it. So we proportionately so there are different routes. So we proportionately, based on that extra cost, we will divide the routes divide the total trip volume into different routes. So if ai is in the minimum cost route, then delta di is equal to 0 and fi equal to 1. So if it is already on the minimum cost route, so then delta di is 0. That means there is no extra cost, and fi is equal to 1. So there is no split. And nodes on costlier routes have delta di greater than 0 and fi lesser than 1. So that means if there is extra cost, then there are multiple routes, and then there is a split. So that's why fi is lesser than 1. The shorter routes are favored over, and of course shorter routes are favored over more expensive ones. So Dials proposed a double pass algorithm using a logit type formulation which split trips from I to j among alternative routes R, where Tij is the total amount of travel between I to j, and then Tij for route R over here is actually Tij into that splitting function, where at the top we are taking e to the power minus omega into the cost of this particular route ijr, the route r in between I and j, divided by summation of all routes between ijr. So between I and j, all the routes, whatever is the cost e to the power that particular cost function, that extra cost function, that is being put in the denominator. And so these are all the routes, and this is only for one route. So this is how we split the different trips. So this is a logit type of formulation. These formulations we have also looked in other cases when we have done when we have used the probability equations to determine how many people would be choosing which alternative and so on. So, we have seen similar kind of equations earlier as well. So, finally, we look into the stochastic usual equilibrium, which are called SU equilibriums, where root choice considers not only the variability in perceived root cost like we were discussing till now, which is basically the stochastic part, plus it also considers the capacity restraint effects. So, when both these cases are taken together, then we get stochastic usual equilibrium. So, stochastic usual equilibrium models seek equilibrium where each user chooses the route with the minimum perceived travel cost and no user has a route with lower perceived cost, and therefore, all stay with their current routes. So, this is similar to Wadrow's first principle. Only thing is we are considered the minimum perceived travel cost by each user. So, that is how stochastic usual equilibrium varies from normal usual equilibrium, and this differs from Wadrow's usual equilibrium since each driver define travel cost individually instead of using a single definition of cost applicable to all drivers, which was in our Wadrow's first principle. So, these are some of the references you can study. And to conclude, while Wadrow's equilibrium assignment has been discussed in this lecture, we have already covered a few capacity restraint assignment techniques in the earlier lecture, and these models try to approximate the equilibrium conditions to a certain extent. But if we want to go into more advanced assignment techniques, we have to look into the equilibrium assignment techniques and compared to the capacity restraint assignments, and then we can also look into SU techniques as well. And then once we have done with the vehicular assignment along different routes, then we also need to do transit assignment, and transit assignment is also undertaken similar to vehicular trip assignment, but however this is more challenging and computationally also it's more challenging. The reason being we have got that means the capacity is provided not by a particular link, but the capacity is dependent on number of transit vehicles that are along the route, and then there is dynamically there is lot of variation in those routes, and plus whenever we have a transit network, people can have difficulty choosing between two alternative routes which overlap each other and so on. So, that means there is also cost. When people consider cost while traveling, they also consider different forms of cost like number of transfers, number of in-vehicle, the amount of in-vehicle travel time, the out-of-vehicle travel time and so on. So, in that way transit assignment is also needs to be undertaken, but compared to the previous normal vehicular assignment, it is a little bit difficult. Thank you.